Now let's look at some elements that have got either partially or completely filled D subshells. Now the D block, which we haven't ventured into yet, is here. So when you're moving across this part of the table, you're filling up S's. This part of the table, you're filling up P's, but here you're filling up D's. So let's pick an element in here. How about iron? And let's do its configuration. And from now on, let's do them with noble gas cores, because life is short and it's so much quicker that way. So what's the noble gas core that is in the center of iron? To answer that question, you look at the end of the previous row. The noble gases are the elements that are in this last column. The one that's on the end of the previous row from iron, here's iron, is argon. So I'm going to write down an argon core. Now I can start counting from potassium. 4s1, 4s2. And now when I start counting into the D block, there is a little irregularity. We've noted this before. You think that things in the fourth row should have principal quantum number 4, but you start to fill in the 3 Ds here. So scandium, Sc, starts to fill in 3 Ds. So this is 3D1, 3D2, 3D3, 3D4, 3D5, 3D6. Now when I write the Ds, watch how I do it. D's come in 5s, always. So I said 6. So 1, 2, 3, 4, 5. I spread them out and line them up. 6, and I only start bunching them up when I absolutely have to. So there are 6 in there. So this is the orbital diagram for this. Now, you may notice that something new is happening here. One is that the valence shell is filling up before this part that's underneath the valence shell is filling up. And we really have 3 pieces here. We have the valence shell, which is the highest numbered shell. 4 is higher than 3, so this is the valence. We have the core, which we're familiar with. It doesn't do anything. It sits there like a rock during chemical reactions, so we're not too interested in it. But what's all this now? Well, when you're filling up Ds, and we'll see later Fs, you get something that's in between the core and the valence. And they call this the pseudocore. So it's outside the core, but it's not in the valence shell. It's a layer in between. And that makes the behavior of elements that are in the D block a little more complicated than elements that only have S and P electrons. And it seems a little bit unnatural to have the valence, which is the outer shell, buried under the pseudocore here. So people do this, do something else. They call this the fill order. And it is perfectly okay for you to write the diagram down this way. This is correct. But people also like to write it down in shell order. And in shell order, you would put the shells outside the core in numerical order. So you would write this as argon 3D. I'm just copying it down. You can write it like this. Now it's in shell order. And actually the shell order has some advantages. It's not just sort of a picky thing that people do. it has advantages, number one, because this actually reflects the energies of the subshells. Once you start to put electrons in the 3D, these electrons can all interact with each other, and they change the energy of the 3D subshell. And it actually, after it is filled to this extent, sinks down to lower energy than the 4s. So the 4s really does become the outer shell. So this is a more accurate depiction of what's going on in the atom than this is. This is the fill order. This is the shell order. Now, another thing you can do with the shell order is, if these are the outermost electrons, when you form an ion, you can start taking electrons out of the valence shell over here. So, if I wanted to write the configuration, and we'll do this a little bit later, of the iron 2 ion, here I have the iron atom in shell order, and the +2 tells me take away 2 electrons, and I will always take them from the right. And I can do this if I write the configuration in the shell order. The configuration of this ion would be that I've taken the electrons out of the outer shell. So when you're forming an ion, you take them out of the valence shell first, and then you dip down into the lower shells. There is also an iron 3 ion, and it has 3 missing electrons, so you take away 1, 2, and then you come down and take away 1 of these. Now, which one do you think you take away? Remember, spread them out and line them up. That's the one that is the highest energy. If you took away 1 of these electrons, you would have them all spread out and lined up, and you'd have a lower configuration. So the configuration for iron 3 looks like we took away these 2, and then we took away that paired up one, and that left us with this. Now, one way that you can characterize these things, describe these things, is to count how many unpaired electrons you've got. We'll say these are paired electrons and these are unpaired. So your atom has got 4 unpaired electrons in it. Your iron 2 ion also has 4 unpaired electrons in it. And your iron 3 ion has 5 unpaired electrons in it. Now these things act like little bar magnets. So you could tell the difference between this configuration and this configuration by weighing the ion in a magnetic field. If you weighed this in a magnetic field, its weight would be different than if you turn the field off. And same thing with this, but less so. So this one is more magnetic. It would have a greater weight change when you weighed it in a magnetic field than this one would. All right, so with Ds, you have to be careful when you're counting into the subshell that you just use the row number for the number that goes in front of the Ds. You use one less than the row number. Let's do another one. How about, let's do zirconium. Okay, so ZR. So to get ZR started off, we are going to have to look at the end of the previous row. So here's zirconium. What's on the end of the previous row? Krypton. So it's got a krypton core. And now we can start counting over here. 5, this is 5s1, 5s2. Whoops. Get ahead of myself there. Okay, there's a pair in there. 5s2. And what's starting to fill here? Well, the 3Ds started to fill here, so the 4Ds are filling here. So remember, the Ds have one less than the row number. So this is row 5, and the Ds have one less than that. This is 4D that you're filling up here. 4D1, 4D2. So there's a zirconium atom. Now, what if you had to put it in shell order? Here it is in fill order. In shell order, it's going to be so there's a zirconium atom in shell order. Now I can see that these two electrons are farther away from the nucleus. They're in the outer shell. And when I take away electrons, I'm going to take them from the right, from the outer shell here. So if I had to guess what kind of ions that zirconium would form, there's 2 electrons here that are farther away from the nucleus than all the others, so they come off a lot easier. So if I wanted to write the configuration for a Zr plus 2 ion, it would look like a krypton core, and then you have your 4 Ds. I'm going to take away the 2 electrons that are there, so this will be empty now. And all I'm left with is that. You might also guess that you could have a zirconium plus 4 ion pretty easily. If you took off 2 more electrons, then all you're left with is the krypton core. The 4D and the 5s would be completely empty. So you could just write this down. Now when you're writing these things down, you don't have to write down the empty ones. So I could just not write this down if it's empty, but I would have to write down the rest of the empty Ds, all right? So if a whole subshell is empty, feel free to leave it off your configuration. But if part of a subshell is empty, still write all the orbitals that are in the subshell. So this is the right way to write this down. So you're starting to see some of the things that we can do with these configurations. What we did here was we predicted what the most common charges for ions of zirconium should be. Then we could go and do experiments and see if that's true. So we can make predictions with these electron configurations. Now let's do one more. Let's do thallium. This is a notoriously deadly element. It's very poisonous, and it's hard to trace because it's not that common. People aren't that familiar with it. So when they detect it in a poisoning victim, you're pretty sure someone was deliberately poisoned with that. There have been many cases like that where people use thallium that evil way. Okay, so let's do the configuration. There's the thallium. TL it is. So I have to look at the end of the previous row, and I see a xenon there, Xe. So this has got a xenon core. If I'm going to start counting then at the xenon core, I'm going to go over here to 6s2. 6s1, 6s2. Okay, so now I'm here. Now we got a bypass to go through here, so we're actually going to be doing more than just D's with this example. We're going to be doing some F's. If I come down here, it says 57 to 70. I see 57 is here. Here is where I'm counting. And notice that these are the 4Fs. We've talked about this before when I drew the table for the first time. So really I have 4Fs counting here. So I took the bypass down here. This is 4F 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Just like we said before, there's 14 electrons that you can fit into an F subshell. And there's 7 orbitals in an F. All of that is a 4F. And I counted 14. Spread them out and line them up. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I have a completely filled 4F shell here. Okay, now I'm picking up here. Now which D is this? This was 3D. This is 4D. This must be 5D. 5D 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5D 10. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so now I am here at Mercury. If I'd stopped here, I'd be at Mercury. Thallium is one more. And what's over here? These are the 6p, so it's a 6p1. So I have to go down to the next line. (6p1). So that's thallium. Now this is in fill order. Let's put it in shell order. Xenon core. I'm going to put the 4Fs, then the 5Ds, and then the 6S and the 6P. So seven orbitals in the 4F with 14 electrons in there. I'm going to just copy them over real quick. Then the 5D comes next. With 10 electrons in it. Then the 6S with 2 electrons in it, and then the 6P with 1. So, question. How many unpaired electrons are in a thallium atom? 1. How many valence electrons are in a thallium atom? Well, this is the valence part right here. So there are 3 electrons in the valence shell. That's the outermost shell. How many electrons are in the pseudocore? Let's see, this is the valence. This is the pseudocore, because it's outside the core. Well, I have 14 here and 10 more here, so there's 24 electrons in the pseudocore. How many electrons are in the core? Let's see. 54. I can look at the core's atomic number and answer that one really quick. So let's count up our electrons. 54 electrons were in the core, and we said 24 were in the pseudocore, and 3 were in the valence. Now here's a check to see if I miscounted anywhere. If I add these all up, I should get the atomic number of thallium, which is 81. And I do. Okay, so I didn't miscount anywhere. So this is one way that you can you can double check. Now, when I give you these things on the test, and this will be exam 3, not exam 2, I will probably ask you to fill in the blanks. How many electrons are in the core? I won't ask you to write this down, right? It's kind of hard to do. You'll have it on your scrap paper, though. I'll say count how many electrons you have in your core, your pseudocore, and your valence, and tell me that. And then I'll know whether you got the configuration right that way. So I'll ask you things like that on tests on exam 3. Alright, so if you can do this one, you're in pretty good shape. In the next video, I am going to do more examples that include the F block. And we'll take a look at a few more ion configurations with that as well.